Hello everybody, this video is going to be about salts, which is an application of our acid-base chapter. So the very first thing I have to say in this lesson is that you absolutely have to have your strong acids and bases memorized. If you don't have your strong acids and bases memorized, you can't do this lesson. So maybe it'd be a good idea to pause, go work on memorizing those and come back in a little bit, but make sure you have a good familiarity with your strong acids and bases so that you'll recognize them and you'll recognize weak ones when you see them. So first, what is a salt? A salt is something that forms when you react an acid and base together. We're used to thinking of salt as just being sodium chloride, but sodium chloride is just one type of salt. There are other types of salt. You can see here we have an ionic compound formed at the end, cation and anion. We had our bases and acids reacting with each other. You get water and a salt is produced. The thing is, when we take these salts and we dump them in water, we have to think about what's going to happen. They're going to dissociate, aren't they? If I have a jar of salt, regardless of what type, right, I dump it in my water, ions come apart. And that's not the end of it. That's where we're used to stopping our thinking, right? We're used to thinking, oh, no, they've dissociated. Maybe we do something like a net ionic or something, right? But we now have to take this a step further, and we now have to think about what happens when these ions start interacting with water. Sometimes they're going to do what's called hydrolyze. Hydrolyzing means they can react with water and another reaction occurs. So you can see here we have an ammonium ion interacting with water. It donates one of the hydrogens and you get ammonia and you get H3O plus formed. The thing is, this hydrolyzation is not going to happen all the time. Not everything hydrolyzes. So we have to have ions that are strong enough for this to happen. So let's look at some of the scenarios. When we dump our salt into water, now we're looking at some dissociated ions and we want to know if they react. One option is that the ion hydrolyzes and the resulting solution becomes acidic because this here hydronium is formed. Another option is that our ion hydrolyzes but goes the other direction and takes one of the hydrogens off of water, which results in hydroxides being made, so the solution would become basic. And there's a third option. The third option is it's not going to hydrolyze. Nothing happens. And if there's no exchange of those protons occurring, we're not going to end up with a change in our pH, are we? So we'll end up with just a neutral solution. So understanding that our ions could react with water is unfortunately not the hard part, okay? The hard part is recognizing whether something will result in acidic, basic, or neutral. Knowing whether the ion has the ability to hydrolyze requires that you know your strong and weak acid bases and that you can recognize conjugates. So, if we want to know whether something's going to hydrolyze, we need to kind of think about our options here. If you have a strong acid, the strong acid turns into a weak conjugate base. And if that resulting thing that's made is a weak base, it's not going to hydrolyze. If you start with a weak acid, it's going to turn into a strong conjugate base, and that can hydrolyze. So if you have a strong base, your ion would be a weak conjugate acid, right? Not going to hydrolyze. But if you have a weak base, you'll end up with a strong conjugate acid, and then it does hydrolyze. So the key here is knowing your strongs and weaks, and then understanding that they're going to dissociate into the opposite, aren't they? Strong acid turns into a weak base, etc. So let's stop and kind of think about, well, why does the strong turn into weak, and why does weak turn into strong? Why do we have this opposite situation here? And what we have to do is think about how much of this stuff is dissociating. If we have a very strong acid like this, most of the acid will be broken apart. It's going to be dissociated, right? It's going to be turned into our products, which means that this is a very product-favored equilibrium. My equilibrium lies very far to the right. So why on earth, if it's trying to dissociate, why would that chlorine go around ripping off hydrogens from water? It wants to just be a chloride ion floating around. It's not going to try to go backwards, right? And so this chlorine is not going to choose to take hydrogens back. So this ion here, while yes, it's technically a base, it's not very strong, meaning it's not going to capture up those protons and revert back into hydrochloric acid. So, when we have salts and we want to know the pH of that solution, there's a lot of steps here, okay? First, you have to figure out where those salt ions came from. Where'd the cation come from? Where'd the anion come from? Which acids and which bases are we talking about here? Then you have to figure out if those ions are going to hydrolyze. So if they came from something strong, then the equilibrium is going to want to lay towards the dissociated side, which means that it's not going to go around trying to hydrolyze. So you'll just get a neutral contribution. It won't affect the pH. But if your ion came from something weak, then that means it will want to go around and stay bonded, right? And so it will hydrolyze in an attempt to be on that side of equilibrium. And depending on what it is, that could either result in it being acidic or basic. So here's one more chart. We're going to have lots of charts for this lesson. Our strong acid turned into a weak conjugate base, and that ion is not going to hydrolyze. So that ion's contribution is not going to have an effect. It's just going to stay neutral. A weak acid results in a strong conjugate base forming. It is going to hydrolyze because it doesn't want to be all by itself. It wants to go take back a hydrogen, right? And when it rips a hydrogen off of a water, we're left with hydroxide, which is going to make the solution basic. If we have a strong base, it'll turn into a weak conjugate acid, which is not going to hydrolyze, so it won't have an effect on the pH. If you have a weak base, it turns into a strong acid, so it will hydrolyze because it wants to be on that side of equilibrium, will result in it being acidic. So what you have to do for the cation, and then again for the anion, is see what kind of contribution it's going to have. You have to do this twice. You have to do this for the cation and the anion. And then you have to think, okay, I have these two ions. They're each having some effect. And what combo of effects do I have? If I have something that's acidic and neutral, for example, I'd end up with something acidic. If I have basic and neutral, I'm going to get basic. Neutral and neutral would get neutral. You get the idea here? But the big deal is, what if you have an acidic contribution and a basic? One ion results in acidic and one results in basic. You have to see which has a stronger effect, which one's going to win. You got to compare your Ka and your Kb. You have to see which one dissociates more. Are you going to have more dissociated acid, or are you going to have more dissociated base? And that will tell you which one wins. Okay. So, when it's time to compare our Ka and Kb, if your Ka is larger than your Kb, then it's acidic. If your Ka is smaller than your Kb, then it's basic. If they're identical, it would be neutral. Now, one thing is, like everything, right? It's not black and white. There's some gray area. Your Ka and Kb could be really, really close, but not exactly equal, right? So, for the most part, the problems we have will make it pretty straightforward. One issue we have is that they do not often give you Ka and Kb for the conjugate pair that you're interested in, right? When you're looking for these values, you may have to do some manipulations. Do you remember me talking about Kw? That's where this is going to come in. So if you want Ka of an ion, you're going to have to look for the base that it came from. If you want Kb of your ion, you're going to have to look for the Ka that it came from. And now our brains are just completely scrambled, aren't they? I think salts and some of the other topics in acid-base are literally just testing if you can keep calm, if you can kind of keep track of which number went with what, which ion came from where, right? It's about being tidy with your work and tracking what you're doing and knowing what your little baby steps were that got you from one thing to the other. Each step's not hard, but keeping calm and keeping track of it is tough, okay? So, for example, I want to know what the Ka is for an ammonium ion. But I have no idea what that number is. I'm not going to look it up. I don't have access to that chart. It's not in the practice problem. Instead, they tell me this. They say, we don't know what the Ka is for that ion, but what I do know is that NH3 has a Kb of 1.8 times 10 to the minus 5. So I can use the relationship that you see at the top of the screen, and I can understand that NH3 is the base and NH4 plus is the acid, that this is a conjugate pair, and this relationship, when I multiply my numbers together, results in Kw, which, because we're assuming we're at the right temperature, right, is 1 times 10 to the minus 14. And then you can solve for the Ka of your ion. So we've already learned Kw calculations. We've already learned conjugates. And now we're using the idea of conjugates in Kw to get us numbers we wouldn't have had access to before. All right, let's try some practice problems. It's going to take a lot of practice, okay? When we block out our pacing for this chapter, you may notice we spend a lot more days on acid bases than some of our other chapters. We need practice. I know we're getting towards the end of the year and everybody's getting burned out and the weather starts getting nicer and everybody would rather be outside. But you gotta keep your eyes on the prize, right? We're almost to that finish line. Whatever sports metaphors you want, right? We gotta push through, okay? So, lots of practice. Is potassium bromide an acidic, basic, or neutral salt? So I need to think about the ions that are present. I need to think about where those ions came from. Potassium can be found in a strong base, can't it? Since potassium can be found in a strong base, that means the potassium ion is going to be a weak acid by itself. Potassium is not going to go around making much effect. It's not going to hydrolyze. So it will have a neutral effect. Now, where might you have seen a bromide ion? Well, you can find bromide in hydrobromic acid, can't you? So if this is a strong acid, Br- is a weak base. It is not going to go around stealing hydrogen, is it? It does not want to be together. It wants to be dissociated. It's more favorable to be dissociated, which means it's not going to hydrolyze. So it has a neutral effect. Now, can some people right away at the beginning of this lesson do this all in their head and keep track of it all? Sure. I wish I was one of those people. I have never been one of those people. I like using little shorthand and little arrows and, K comes from KOH. And then I label that, SB for strong base. So K is WA, weak acid. If you got to label stuff, do it. There's no problem with that. Do it fast so you don't lose time, right? But it's not bad. Just because your friend can do it in their head doesn't mean that matters. Who cares? Write it out if you have to. Maybe if you write it out enough times, you won't always have to. Okay. So we know that we have two neutral effects happening. So that means KBr is a neutral salt. I dump that in water and my pH is not going to change. All right, try this one. See if you can walk yourself through to figure out if these ions would have a neutral or acidic or basic effect. Pause the video so you have time to figure that out. All right, we have our ions. Potassium came from our strong base, which means it'll be weak, which will have no hydrolysis, so it'll have a neutral effect. But here, this came from a weak acid. So this will be basic, won't it? It's going to hydrolyze and have a basic effect. So, if we have something basic and neutral combined together, the overall effect is going to be what? It's going to be a basic salt. I dump that in water, it'll turn basic. All right, try this one. Pause and give yourself time to figure it out. All right. We have our ammonium ion, we have a bromide ion, and we need to think about where they came from. This, if it lost one of these hydrogens, you would see it came from ammonia, which is a weak base. So this will be acidic, it will hydrolyze, and result in an acidic contribution. Bromide came from hydrobromic acid, strong, so the ion is weak, so no hydrolysis, so it's neutral. So now if we have something that's acidic and something that's neutral, turns out that that salt would end up being an acidic salt. Okay, one more. Oops, change that color. All right, pause and try to figure this one out. So we have ammonium ion here, we have cyanide ion over here. We just saw that ammonium came from ammonia, so it's weak, turns into strong, so it hydrolyzes, and so we have an acidic effect. Cyanide, you can see, came from a weak acid, which means it is a strong base, so it will hydrolyze, will have a basic effect. Uh-oh. That's the bad combo, right? That's the combo that requires more work from us, doesn't it? Now, if I have acid and base contributions, I need to stop and I need to compare the values of K. So, I look up in a chart and I can find the Kb of NH3, which is the conjugate of my ion. I can look in a chart and find the Ka for our conjugate of our ion. But now I have to convert them, don't I? So I'm going to use the Kw, rearrange, and now I know what the Ka is for my ion, for both. Now I can compare the K values for the ions. I can't compare these ones, I gotta compare the ions. So now I can see that Ka is smaller than Kb. So base wins, it's a basic salt. Sometimes people will ask me way at the beginning, like, well, how do you know if it's a weak acid or weak base? Well, if it's not a strong one, by default, it's weak. Okay. Now, you need to be very careful that on your AP work, you don't try to compare the Ka and B of the conjugates. I've seen them be very picky that you must convert and you must use the conjugate of the ion. Sorry, the conjugate ions, right? You gotta use the actual ion K values here. You have to convert. All right, I wish we were done. We are not done. We've just decided if it's acid, base, or neutral. That's some pretty big categories there, isn't it? We need some actual numbers. We need some actual pHs. So I'm going to put a list of steps up. And everything we just did, all that work, is step 1. So the last 24 slides is all just step 1. Once you figure out which thing's being hydrolyzed, then what you're going to have to do is write out an actual reaction for it, for that ion reacting with water. And then, what do you think we're right back to? More ice tables. once you have your ice tables, you can find your concentrations, and then once you have concentrations, then you can do normal pH calculations. So I've taken the concept of salts and all our weak, all our ice table stuff, mushed it all together into these big, crazy mega problems, okay? So let's try one. We're just going to do one. It'll be enough, okay? What's the pH of a 0.25 molar ammonium nitrate salt solution? So step one, we need to first figure out if this is going to be acidic, basic, or neutral. Why don't you pause the video and figure that out? What type of salt will this be? All right. I have my ions. I recognize that this came from a weak base, which means it was an acid. It will hydrolyze with an acidic effect. Nitrate came from a strong acid, which means the ion itself here is weak. No hydrolysis, neutral effect, which means that this is an acidic salt. Now that I know which ion is going to hydrolyze, I need to write an equation, okay? I need to write the hydrolysis for my ammonium ion reacting with water. Why don't you pause and try to write that chemical equation? Keep in mind it's acidic. So if this is acidic, it must be getting rid of a proton. And if it's reacting with water, that means water must take the proton. And we get that. Way back when we first started writing acid and base reactions, we were used to just writing something like NH4 plus loses a proton and you get NH3. But we now have to understand it's more complicated than that. We don't just have a bunch of protons floating around, do we? It's mixed with water. The proton's attaching to that water. This hydronium here is our acid, right? So now we need to start doing equilibrium calculations, which means we need K values. But I don't have a K value for this ion. I have a Kb for NH3. We know our Kw. So now you plug in and you solve for Ka of your conjugate, right, of your ion pair here. Why don't you pause and try to do that? All right. Now that I have my K value, now I can do an ice table. Do you remember way back to Honors Chem when you thought ice tables were as long and as terrible as it got? Okay. Now you see an ice table is just a baby step, isn't it? Why don't you try to set up an ice table for this equation? And you have your starting concentration up here. Now you may notice we don't have anywhere in here for our nitrate ion, do we? Because it doesn't matter. It's not participating in this reaction. It's a spectator. Pause and set up your ice table, and then you try to fill in your numbers. Unpause when you're ready. All right, so we started with 0.25. Water is not it's not included. It's a liquid. We had no products when we started. 1-to-1 ratio, which is nice. I'm going to have a minus x, a plus x, and a plus x. The nice thing is I can use my 5% rule and I can ignore this piece right here. You don't have to put that as a row. I like to when I'm trying to explain things, but you don't have to. I have my Ka, products over reactants, water is not included. I have my simplified version thanks to my 5% rule. Now, you have to somehow tell people that's what you're doing, okay? You gotta justify that simplification. You can just write 5% rule. I'm fine with that. They may ask you to give more detail maybe, but I think it would typically be fine to just indicate you're using 5% rule. Solve for x. The nice thing is, since our answer was just x, we're kind of done at that point. But we're not done, are we? We're not completely finished with the question. Read the question again. The question didn't ask what the concentration was. It asked for the pH. So now you can finally use the concentration you have. Take the negative log, get your pH. The concept is the same for bases, right? But you may have a little bit trickier time recognizing the equation. And then you'll be solving for pOH, so then you'll have to convert that to pH. So just a few extra little pieces mixed in if it's a base. You always want to cross your fingers it's an acidic salt. Those are typically the better ones. Now, I just have two more little things that I want to cover. I feel like they don't come up often, but, you know, if you see it once or twice, it's unique enough that I don't think we need a ton of practice on, but you could scrounge up a couple points here and there if you can remember it. So, sometimes you may have metal ions that have large charges, 3 and up, okay? And those large charged metal ions, highly charged, can end up hydrating, okay? So they can interact with water. Water kind of surrounds them, right? And it will function as an acid. So you may see some funky metal containing compounds like this, and you should know it's an acidic contribution. For example, you would get something really crazy looking like that, where waters surround the ion, but it's still charged, and you end up with this chlorine, this chloride. Now this part here, this funky looking ion, gets even crazier. And one proton pops off. So your charge goes down by 1, and you have a proton floating around, and now you have aluminum with a hydroxide and several waters. Now, I don't expect you to know how many waters can hydrate around a cation, but you should understand that it happens. And if they give you the reactions, you shouldn't panic when you see funky looking things. You can look and kind of go, oh yeah, I remember. It's gonna hydrate, and then we're gonna kick out a proton. All right, last one. Sometimes you may have some strange looking acids. Look at these for a minute. pause the video and just ponder and think about why might these be getting more acidic as you go to the right. What about that makes the hydrogen come off easier? All right, do you notice what high electronegativity there is in the little yellow boxes that I highlighted? And the electronegativity difference compared to that poor little hydrogen is getting greater and greater and greater and greater. We're pulling harder and harder on these electrons, which means that the bond here is more and more and more weakened as you go to the right, which means it will come off more easily, and if it dissociates more easily, it'll be more acidic. So sometimes they may give you a funky shape like this and ask you to ponder which one might be more acidic. All right, everybody, I know that was a lot for one lesson. There's not really a good way to shrink it up. I've never found a good way. I think just getting it all done is the best way to do it. So I know it was longer than you would hope, but I hope it was helpful. All right, everybody, bye.